You know, we have done alpha, beta, gamma radiation thing, and we have gone through the properties and the characteristic of alpha, beta, gamma radiation. Now, today we will proceed with a new topic in the same chapter, and that is basically uh, nuclear fission or fusion. Now, first and important thing is okay. Now, important thing is this reaction means, as the name suggests, nuclear fission. Fission means breaking of a bigger nucleus into smaller nucleus, or you can say breaking of a parent nucleus into daughter nuclei, right? It means that one big nucleus broken down into two smaller nucleus or nuclei, and definitely lots of energy will be released in this. For that purpose, the reaction which is used here is called fission reaction, and mostly this reaction is actually performed in nuclear reactor. This reaction is actually for the atom bomb, you can say. The atom or the nucleus, the element which is used for this reaction is called uranium 235. But if you cannot find uranium 235, then plutonium can also be used for the fission reaction. If I read it for you, they can say that we can split a nucleus. Though the process of nuclear fission, we can split a large unstable nucleus into two smaller particles. For example, uranium 235, which is a naturally occurring isotope of uranium, this is made possible through the use of nuclear reactor. Now, definitely you have to do it by some means, and the means which is used there is called as nuclear reactor. Nuclei undergo induced fission. Nuclei does not or do not often split up on their own. Now, very important thing is there are some nuclei which do perform this fission reaction on their own. Remember that we are not talking about that nuclear reaction which actually performed on their own. So we are talking about the one which is actually performed. So instead, they have to undergo induced. Induced one, the one by some means you do that. During this process, they absorb neutron, which leads to fission. So how do we perform it? We perform it by using bombardment of neutron on an isotope of uranium, like for example. Okay. So that's how we do this. Now, important thing in this case is how do this process actually works? We bombard a neutron, okay? And when you bombard a neutron there, the unstable nucleus absorb neutron at the first step. Then nucleus split up into two daughter nuclei. Once again, neutron has been absorbed by the nucleus, will split into two smaller daughter nuclei. Energy is released through the fission reaction. Now, this is the process. I want you to write from this place and also till here. Please write that one. And then we'll see. First, write it down.
Sir, can you explain the example?
Yeah, I will. I will. First, write it down because we have an equation here which I will definitely explain. But I want you to write this as well. Then I will definitely explain in full details. Once you write it, I will just let me know. Today, inshallah, Aziz, I'll try to finish this chapter and then we will start electromagnetism and electromagnetism as well. Remember that whatever we are talking here is we are talking about induced fission reaction in which fission is performed by bombardment of the neutron on a big nucleus, and then this nucleus will be broken down into daughter nucleus. All right.
Sir, in the nuclei induced fission part, they're talking about like before the nuclei split, right? Like when it's still a nucleus, that's when the induced fission happens.
Absolutely. You know,
Okay.
induced fission means it's a process. Induced means which you or me we did it. So Definitely, there must be a nucleus first. And then once the nucleus is there, we bombard neutron onto that, and then this reaction actually starts. Okay. Now let's see that. If you ask me here, I better explain it here at this point. Check it out. Check this equation here. If you see that, what is happening? This is your uranium nucleus, right? You bombard this uranium nucleus with a neutron, one single neutron. As soon as this neutron hits the uranium, first of all, the uranium becomes unstable and it converts into uranium 92 236. Then, definitely, due to different forces and everything, it blasts or converts into its daughter nucleus. One is called the barium, another one is called as the krypton. Along with that, you will have three further neutrons which are actually emitted out, and lots of energy is released in this case. So, this is what the fission reaction is all about. This energy can be used for different purposes. We can store that energy for the electricity, or we can use that energy for atom bombs as well. I mean, we can make atom bombs with that as well. In the equation format, this is the way of writing this equation. You can see that uranium 235 is bombarded with one neutron, and it gives you a krypton. That's a element actually, and another element that given by this one is called barium. Along with that, there are three further neutrons, and lots of energy is released. Okay, understood, Ibrahim?
Okay.
I want you to write this and also write that as well. Process of the nuclear fission. They have written like this, that neutron absorb neutron. In this heading, what they said is most fission reactions, the unstable nucleus will absorb neutron as the first step. Then nucleus split into two, right? Once the neutron has been absorbed, the nucleus will split into two smaller daughter nuclei. Energy is released to the fission reaction. Now, what energy is that? Neutron and gamma rays are emitted. So, nucleus will also emit two or three high energy neutrons when the fission reaction is happened, as well as two or three neutrons. Gamma rays are also emitted. Okay.
Sir, I don't understand the third point where they say the nucleus will emit two or three high energy neutrons as well as two or three neutrons. Like, well, is is this like after the reaction and during the reaction?
No, no, yeah. This is, see, what they're saying is nucleus will also emit two or three high energy neutrons when the fission reaction is happened, as well as two or three neutrons. Gamma rays are also emitted. What they're saying is, along with these three high energy neutrons, gamma rays are also emitted. It didn't mean that neutron again and again emitted out. Along with the neutrons and along with the everything, you will have energy released as well, and that is gamma rays, you can say, right?
Okay. Okay. And there's no fixed amount for gamma rays, right?
Definitely energy. See, energy, because you asked me a very different kind of question. See, gamma rays, there are not fixed amount, definitely, and there is a reason for that. I will tell you in just a bit. If you write this one, I want you to also write this equation, please. This is the equation of the nuclear reaction. I'm talking about this equation, not the one at the top, not the diagrammatical way. The way of writing an equation is this. So you have to write this equation. Huh? So now, once you write it down, everybody wrote it? Yamna, Armina, Safila, you can get this recording as well. That will help you a lot. Okay, but continue from where we just actually started. So what exactly
Sir,
happened? Yeah, you're saying something?
is this fission?
Yeah, it's a fission.
Okay.
Now, important thing is, once again, how do fission actually occur? One single neutron is bombarded on a uranium nucleus, 92 235. As soon as we place this neutron very near to uranium, or you can say uranium 92 235 absorb one neutron, It gives us byproducts. I mean, first of all, it gives us two products. One is krypton 3689, one is a barium 56144, and as a byproduct, you got three further neutrons plus lots of energy. My point here is, can I call this reaction as a chain reaction? How many people are agreed that this reaction is a chain reaction? Yes, anyone? Why I am saying this is a chain reaction? That of course, when you have millions and millions of atoms, let's suppose you got 50 grams of uranium present somewhere. It means you have millions and millions of atom available over there. So if you release with these three neutron, each neutron will go in single atom or single nucleus and do the fission reaction and release three further neutrons. So it means that these three neutrons further when go into three further further uranium atoms will release nine neutrons. So that reaction will continue until all the uranium will be finished. So that it means that that fission reaction is a chain reaction. Once you start this reaction with one single neutron, then this reaction will not stop and it will continue and it will go on and on and on and on and on and on and releasing lots of energy as a result. Now, an important thing. You have just given one neutron and it gives you three neutron along with lots of energy. What do you think this reaction is an endothermic reaction or an exothermic reaction? How many people knows what is the exothermic or endothermic reaction? Armina, what is endothermic or exothermic reaction?
So endothermic reaction is when the surrounding heat is taken in process,
You can say input,
and
you can simple.
exothermic is when the heat is.
Okay, she's absolutely right. In other
Yes, sir.
words, yeah, no, that's fine. She's absolutely right. Input energy or energy provided is given, then the output energy, that type of reaction is called as endothermic reaction. If input energy is less than the output energy, that kind of reaction is called as exothermic reaction, right? Now, Ibrahim, what do you think about this? Is it an exothermic or endothermic reaction? You're only providing neutron to this reaction. So what do you think, the energy release will be more than the input energy, or will that be less than the input energy? Safiullah or Yumna?
It will be more.
It will be more, definitely. So remember that this reaction is an exothermic reaction because the energy produced during this reaction will be used for different purposes. Like we can produce electricity through that, or you can use it for the atomic bomb as well. Now, an important point which I want to clear at this point is, if this energy can be controlled, the energy can be used for so many purposes like electric energy or so many things. But if it is uncontrolled reaction, then it will be an atom bomb. So it means that nuclear fission chain reaction will be of two types. One is fission controlled reaction, and the other one is fission uncontrolled reaction. I will discuss with you how to control or uncontrol or make it uncontrolled when we will be doing nuclear reactor in this case. Okay. But for the time being, if you control this, it will be controlled reaction. And if you cannot control it, then it will be an uncontrolled reaction. My simple point is, how can you control this reaction speed? Who will tell me? By looking at the equation, how can you say that? How will you control the reaction?
By adding or removing the neutrons.
Yes, not by adding, because you already start with one neutron. You can absorb by any means. If you absorb some of the neutrons or more neutrons, by means of something, it means you can control it. And if you can control it, then you can use that energy for so many purposes, right? But if you cannot control it, then it's atom bomb then. All right. So this is what the nuclear fission reaction is. I want you to write this as well. Product of nuclear fission reaction. Firstly, fission produces products have kinetic energy. The neutrons and two smaller nuclei released in the fission reaction are highly radioactive and will have kinetic energy. The kinetic energy allows the fission products to move away from the original reaction. There is no need to write that. Then gamma rays carrying excess energy, an energy that is not absorbed by the product of reaction is given to the gamma rays. This means gamma rays will move. Also, there is no need to write this. So you have to write till here. Same thing till here. And the last one, neutron can start a chain reaction. The neutron released from the fission reaction will have a kinetic energy. Therefore, the neutrons can move. There is no need to write this. Okay, the neutron released. Therefore, the neutrons can move around. No, you can write that. Neutrons can move around and become absorbed by another large unstable nucleus. This will lead to a second fission reaction and resulting in a chain reaction. Please write it down.
Sir, till where do I start the second point?
Gamma rays carrying excess energy, right? Any energy that is
Yes.
not absorbed by the product of the reaction. Product of the reaction is given to the gamma rays. Very simple. Whatever energy which is not absorbed to the product, I mean, which is not associated with the product, definitely will be a part of gamma rays. That's what it means. It is just to, means, it is only for the written case. You can only write gamma rays carrying excess energy. It means that whatever energy is not a part of product will be a part of gamma rays. All right.
And sir, the third point?
Third point means neutron can start a chain reaction. As I told you, you already got three output neutrons, right? Now these three neutrons will go to further three nucleuses or nuclei of uranium, and then each neutron again gives you three output neutrons. So again, all the neutrons go into further atoms. So it will continue and continue and continue, and that's the reason this reaction is called as chain reaction. One reaction you started with one neutron, and it just carry on and carry on and carry on and carry on. That is the reason we call this reaction as a fission chain reaction. All right. So we have just we have just ended fission reaction. So for further like if you want to go into the detail of that, you can go through the recording. Okay, it's very small recording for half an hour. You can go through because I have to move on, right?
Okay.
Okay, guys, have you finished? Safiullah,
Yes.
Armina, Yamna, Ibrahim.
Yes.
What about Yumna and Armina?
Yes. Sir, I've also written.
Okay, now let's move on. This is what the fission reaction is all about. Now, another reaction is called as nuclear fusion reaction. As the name suggests fusion, it means joining nuclei. So, in this case, two smaller nuclei actually combine or fuse to give you one big nucleus. Okay. Now, what do you think? Will that be easy to join two small nuclei to give you a big nucleus? No, it's very difficult. For that reason, lots of energy is required, and some conditions are very difficult to achieve. Those conditions are required in this case. So, nuclear fission reaction is purely an endothermic reaction in which lots of energy is required. That is the reason this reaction is not possible on this earth, because you need a very high temperature and very high pressure, right? For that temperature to happen, to took place, you just need 100 million degrees centigrade. So And this temperature is only and only available on sun, because this reaction cannot be happen on this earth. So what is this reaction? A nuclear fusion reaction joins nuclei together. The process of nuclear fusion joins nuclei together. This is essentially the opposite of the nuclear fission. Two small nuclei will be joined together to form a large nucleus. The end product of nuclear fusion is heavy. Since we are combining two small nuclei to make a large nucleus, the end product to this reaction is heavy, and this fusion leads to a lots of energy being produced. Remember that energy, lots of energy is being produced, but again, the energy which is provided is much more than the energy which is produced. That is the reason this reaction is a nuclear fusion reaction. Mass can be converted into energy. We have just mentioned the fusion reaction can produce lots of energy. When the two small nuclei join together, some mass is lost. And that lost mass gets converted into energy, which is released as a radiation. There is no need to write the last part, but you just need to memorize it, that some of the mass is changed into energy as the output. Okay. So I want you to write this from here to here. Put a heading nuclear fusion and write this down. And once you write that down, write this equation as well. Along with that, I hope we've written the equation as well. Now, if you see the equation here, there are two hydrogen nuclei. One is isotope and one is a simple one. They fuse to form a helium nucleus, right? So for fusing of hydrogen and hydrogen to become a helium nucleus, it's very hard, and as I told you, very high conditions are required. This reaction is occurring on the sun, fusion reaction. When we will be studying astrophysics, I will tell you in more detail that this is the reaction which is actually essential or necessary for every star of being a star. If that is a star, this reaction is necessary. This reaction must be on the surface of a star. Otherwise, that star or so-called star is not a star. If that reaction is not undergo on its surface. Okay. So fusion reaction. Now check this out. As I just told you the conditions. Very high temperature and pressure is needed for the nuclear fusion reaction to occur. A high temperature provides enough energy to overcome the electrostatic repulsion and found between the positive charge nucleus of each isotope. The same applies to pressure. High pressure are needed to overcome the electrostatic repulsion. The specific conditions require make it very difficult to maintain a practical and economically friendly power station. It means it's very difficult to develop a power station which do perform nuclear fusion reaction on the earth. Okay. So I want you to write these conditions as well. At this point, I want you to put a heading difference between nuclear fission and fusion reaction. Difference between nuclear fission and fusion reaction. On the left hand side, write nuclear fission. And on the right hand side, write nuclear fusion. Ibrahim, what is the first difference between nuclear fission and fusion reaction? First difference, the basic difference.
In
Or
fission the nuclei split apart, and in fusion they come together.
you can say that in nuclear fission reaction, one big nucleus broken down into daughter nuclei, and in nuclear fission reaction, two small nuclei fuse together to give one big nucleus, right? Second difference, it's the equation. of both of them. Safiullah, what could be the third difference?
So can you say the first difference again?
The first difference is big in nuclear fission reaction, big nucleus broken down into its daughter nuclei. One big or heavy nucleus broken down into two daughter nuclei. And on the other side, fusion reaction will be two smaller nuclei fuse to form one heavy or big nucleus. Second one will be the equation. What about the third one? Anyone? Third difference between nuclear fission and fusion reaction?
The conditions.
Definitely the condition. For fission reaction, no special condition are required. But for the fusion reaction, we need very high pressure and high temperature, which is only possible on sun. Very good, Safiullah. Armina, what about the fourth difference? Or Yumna, fourth difference? Ibrahim, which reaction is exothermic reaction and which reaction is endothermic reaction?
Fission is the exothermic.
Absolutely. Fission reaction is exothermic reaction because output energy release is more than the input energy provided. On the fusion side, you can say that it's an endothermic reaction as the input energy provided is more than the output energy released. Anyone have any question regarding fission and fusion reaction?
Sir, can you go over all the points again?
Okay, one by one. The first point, the main difference. Nuclear fission reaction is in which a big nucleus disintegrated or broken down into daughter nuclei. You can say two daughter nuclei because the reaction is different, but you can say one big nucleus broken down into two daughter nuclei, right? While on the fusion reaction, you can say that two smaller nucleus or nuclei combine to form one heavy nucleus, right? This is the first point. The second point is the equation in which neutron is bombarded on uranium and you got krypton and barium along with three neutrons and lots of energy. On the other side, you will have two hydrogen nuclei combined to give you a helium nucleus. Third point, conditions. For fission reaction, no special conditions are required, while for the fusion reaction, you need very high temperature and high pressure to overcome the electrostatic repulsion forces between two positively charged nuclei of each isotope. That's it. The fourth point is endothermic and the exothermic one. So fission reaction is an exothermic reaction as output energy released is more than the input energy provided. Fusion reaction, it's an endothermic reaction as the input energy provided is more than the output energy released. All right, Ibrahim?
Okay, sir.
Right. So This is how we ended up with our nuclear fission and fusion reaction. Now, a new term actually came. We will talk about the nuclear reactor in a few minutes, but let's talk about the uses of nuclear radiations. Now, nuclear radiations are used for so many purposes. Okay. Did we do this topic or not? I forgot to actually. Gamma radiation uses and all this. Ibrahim, did you do that? I didn't think of this. We have didn't do that. So let's do that then. The first one is radiotherapy. So radiotherapy can cause a tissue damage. Doctor must be careful when giving radiotherapy to patient since the gamma rays can kill normal tissues too. Therefore, they need to strike a balance between killing the cancer cell and not destroying too many normal cells. So basically, for the purpose of cancer treatment, we do use these radioactive radiations. Okay. So this is for the use of radioactive radiation. But remember that if you use so much of them, then tissue damage can lead to mutation. If the radiation damage the DNA with the cell can rapidly divide, and this abnormal behavior is called a mutation, where the cell now becoming a cancerous. So remember that these radiation, especially the gamma radiation, do cause the cancer as well. Because what happened when too much cells are affected by gamma radiation, then cells start mutation. Mutation means they become cancerous and they start multiplying themselves. So this may cause you to damaging the definitely the cells, and cell this leads to the cancer inside the human body. Gamma rays are also good explorer. Doctors are able to use gamma rays to explore internal organ due to their weak ionizing power. The main benefit of their tracer is that they allow life-threatening condition to be diagnosed while not ionizing too much tissue. So this gamma rays can be used for the exploration as well. We could put it into human body and we can use it for so many purposes. So at the same time, gamma rays are definitely dangerous, but at the same time, these are the good exploration things and all the things as well. So they are using at the same time, but we have to use it with so much care. Without doctor prescription or without doctor, you can say consent, we cannot use so much of that. Otherwise, it will cause humans to reach to the cancer. Okay. Now, internal and external radiation. Tumor can be treated using either internal or external radiation. The level of danger varies depending on the type of radiation used. Summarized in the table, you need to able to compare. Now, this is very interesting. If you write them, then I will proceed further. So let me know.
So we have to write the evaluation.
Evaluation means the danger, you can say that. Put a heading danger.
We
And
have to write
sometimes,
all these
yeah,
3 points.
yeah, write it in a precise way. Do not write each and everything. So that
Sure.
whatever comes to you, you can write it. Uses and the danger, everything. By the way, first and the third point are the uses, technically speaking. And the second point is the danger of it. That is what we call as evaluation. Uses and the danger. Write just a precise way so that you can understand that. You don't need to write each and everything. Remember that, especially these ones, because they are just for a theory purpose, because they come in our examination. That's the reason I'm giving you time to write it.
So which ones are the uses again?
First and the third one, check it out. Radiotherapy is one of the use, and gamma rays are the good for exploration. They are the major uses. But remember that uses didn't mean that you will use it openly. You have to use them with care because too much usage of these gamma radiation cause a person, cause a cancerous uh, cells inside a person as well. So uses are there, but Don't use without K. You have to use it with K, right? So that is the reason why the uses and the dangers are written under a single heading called evaluation. Otherwise, they should have different headings for that, right? Why these are used for the internal organ things? Because they have less ionization power, and that's what we don't need inside the human body. But they are penetrating, they can go anywhere. So they are also used for the exploration as well. Exploration inside the human body. For internal and external radiations of what? What do you mean by that? Now check this out. In this table, you can see that internally, definitely because alpha radiations are very high ionizing power thing. So very dangerous radiation, easily absorbed by the cell. Beta 1, okay. For external, less dangerous radiations likely to reach to the cell inside the body. For beta 1, less dangerous radiation, less likely to be absorbed. And for external, most dangerous radiation can be penetrating the skin to reach to the cell, causing tissues damage. So basically, for tumor purposes, this is the thing which is written over here. For internal one, I believe we used beta and gamma radiation. And for external use, we used alpha radiations. Because for internal use, alpha radiations are so much dangerous. As I told you already, they are the most ionizing one. So we don't use it for the internal purposes. We use it beta or gamma radiation. So write them as well. So it means that wherever we use it for the human internal body treatments, we don't use alpha radiation. They are very dangerous. We use gamma radiation for that. That is the reason for cancer treatment, we use gamma, not alpha. Alpha are dangerous. Even though gammas are also dangerous, but still, as compared to alpha, they are less dangerous. For external one, we may use alpha, not the gamma or beta one. They are the uses of alpha, beta, and gamma, everyone. So we are actually doing that topic. After that, we have left with only one topic that is called a half-life. Let's see if we can finish that and reach to half-life. So for the further hazards and everything, let's check this out. I'm just reading it. If we think you have to write it, then this depending on the source. For some sources, irradiations can pose risks, whereas for other sources, contamination can pose risks. So basically, they are all are contamination and everything. That's what they're saying is alpha source work in small areas. You don't have to write this all. They are just hazards. Hazards means that they may cause danger, but because it's written over here, that's the reason I have to. But what are the precautions? That is important. That one is important. Irradiation can be prevented. Don't need to write this. We can prevent unwanted irradiation quite easily to keep alpha beta source from irradiation object. We can limit exposures. Workers can limit and monitor their exposure using badges containing photographic films. Sources can be removed by placing the sources into appropriate container. We can keep radiation source away from the object. We can also place them into separate room. Irradiation will stop as soon as the source is removed, whereas contamination can be difficult to remove completely. Protective cloths can be worn, as well as placing source appropriately. We can wear cloths to protect us from radiations. We can wear gloves so that radiation particles do not stick to our skin, or use forceps to handle radioactive substance instead. We can even wear masks so we don't accidentally breathe in the particles. Okay. So this is what we have. I want you to write that. And which material you will be using to put the stuff in and then remove it? Made of what? Remember that the box which you normally put the radioactive material will be made of lead, will be made of concrete. Mostly we do it with the lead. because lead is a good absorber. All right. The material, I mean, the cloths which we normally used to wear are made of lead as well. So important things in these one are remove the sources or less exposure to these radiation particles, or you can say the particles emitting radiations. Protective cloths, use forceps, or remove or wear the cloths made of lead and all these stuff. And if you want to remove these sources, you have to put these blocks into some sort of box which made of lead and concrete and all this. Guys, these are the cloths which normally they wear. Okay. I think so, Ibrahim, you have done this. So let's move on. This kind of thing you can see here. A person normally wear these kind of things. So there are few things I will tell you what to write, not to write. So we can study hazards of radiation to find out the effects on human. So basically, this one we don't have to write anything in this. We have done this that these are used for the cancer treatment. We have write this already in the evaluation. I want you to write this one quickly. Gamma isotopes are used as a tracer. Tomography scanners, isotopes have very small half-life, so need to be produced nearby, and they are manufactured in the hospital and injected to the patient's body soon as possible. So tomography purposes, they are used for. Iodine is used in thyroid glands. A radioactive isotope of iodine can be used to check the functions of thyroid gland, and the radioactive isotopes will be absorbed and traced as it moves into the thyroid gland. Then sterilizing equipment. This is common with the surgical equipment. Sterilizing can be carried out without high temperature. However, it may not kill all the bacteria on an object. So we do use these radioactive isotopes for different purposes as well. So these are uses of radioactive isotopes. That is the heading, uses of nuclear radiations. We have done the first one. I want you to write the ones here. Don't need to write everything here. They wrote positron emission. Don't be confused with that. Just write the basic ones like gamma isotopes are used as a tracer. Just write till here. Would be enough for you. Or if you want to write it till here. There is no need to write, for example, in positron emission.
Sir, I'm done.
Okay. So students, this is all what the uses are. Okay. There are different uses as well, but you can check it further if you really want to go into the detail. But I think that this is enough. Okay. Now, one small topic is there that is called background radiation. Now, what is meant by background radiation? Background radiations are such radiations which doesn't affect too much, and they are always there with us. Okay. And what are the sources for that? Rocks. From the rocks, we can get that. So in air around us, there is always a low level of background radiations. This radiation will comes from various sources. Background radiation can come from natural source, like rocks are natural source of background radiation, while cosmic rays can bring background radiation from space. Food and drink can even be natural sources of background radiations. The unstable isotopes in these sources will lead us to background radiation. Background radiation can come from man-made sources as well. Sometimes the background radiation can come from man-made source, and these sources leads to be from nuclear weapon testing or nuclear accident. Although these are very dangerous sources of unstable isotope, they only make up a small amount of all background radiation. They can also come from medical equipment such as X-rays. Okay, so this is a very small topic related to the background radiation. I want you to write a heading background radiation and write something related to background radiation as well. Write this all, please. So,
Done.
yeah, so today we have done fission, fusion, and uses of, these all. And Now there is one small thing. You know what I was at that time I was telling you about. See, that is how it actually your gamma red. This is your positive. This is your anode, and this is your cathode at that time. So towards anode, if you actually turn up, this is your beta radiation, and if it turns to negative, that is your cathode. It is your alpha radiation, and this is how it turn up in the magnetic field. So this is, yeah, this is the one. You can check it out that both are turning in different directions. Okay. So our new topic will be half life technically. And let me see if I have it right now. Okay. This one we have done that. Okay. Here. I want you to write it at least. We will talk about this later on. There are two, three definitions written under the heading of half life. I want you to write it quickly, please. Half life can be measurement of decay. The half life of radioactive isotope can be help us to measure the radioactive decay of a substance, which is defined as time it takes for a number of nuclei of isotope in a sample to half, or the time it takes for a count rate from a sample containing an isotope to fall to half of its initial level. Students, we will be discussing this in the next class. Yeah. All right.
Okay.
Oh,
Okay. Now here there is a start time, so I think we better stop it here. In the next class, we will be discussing half life and related numericals. All right. So everybody, see you. See you in the next class, inshallah. Allah Hafiz. Take care.